Hey guys, so let's look some more at theoretical probability. So we're still going to be listing out the sample space of chance experiments. That's like all the different possible outcomes. But we're going to be using tree diagrams to represent the sample space, just because it's a different way of doing it that some people might find like more organized or easy to follow. So let's like kind of just practice doing the same thing, but just in a different way. So let's look at the example down here. This is they want us to sort of like see how they're doing it. It says, imagine that a family decides to play a game each night. They all agree to use a tetrahedral die. That's a four-sided die. Not the tetra means four. And so here's a picture of what that looks like. I don't know how well this is going to come up in the video, but it's like a pyramid with three sides here, here, and here, and then one side on the bottom. So it's a die that only has 1, 2, 3, 4, not 6 like you're used to. Okay, so they all agree to use a tetrahedral die where each of the four possible outcomes is equally likely. Each night, to randomly determine if they will play a board game, which will represent with the letter B, or a card game, which will represent with the letter C. The tree diagram mapping the possible overall outcomes over 2 consecutive nights will be developed below. Okay, so the way we do this is first we make a column for each stage in the chance experiment. And so in this case, each stage is a day. Right? Stage 1 would be Monday, where they decide what game they're going to play there. And then stage 2 would be Tuesday, as they decide what game they're going to play there. And so we have a column for stage 1 and a column for stage 2. And then we write, like in a column manner, all the different possible outcomes for each stage. So in this case, on Monday, they could wind up playing a board game, which is B, or they could wind up playing a card game, which is C. Then, for stage 2, we're going to draw a tree from each outcome in stage 1 for each secondary stage outcome that could happen after this. So that's probably confusing the way I just worded it, but as I do it, hopefully it'll become more clear. In stage 1, or Monday, they could play a board game. But then if they play a board game on Monday, on Tuesday they might also wind up playing a board game again, or they might wind up playing a card game. Then we go back to Monday and we say, well, they could play a card game on Monday, but after playing a card game on Monday, they might wind up playing a board game on Tuesday or a card game on Tuesday. And so each one of these like tree branches represents one singular 2-stage outcome. So one 2-stage outcome would be board game, then board game. So we could call that BB, right, for board game, board game. Or they might go board game, card game. So we could call that BC. Or they might go card game, board game. And so we call that CB, which is different from BC because the order is different. And then they might go card game, which we would call CC. And so they've actually completed the same thing that I just did here, but I figured I'd write it out for you because I could explain it while writing it. So here's the book's version of it. All right, so it says here that note, if the situation has more than 2 stages, like if we were doing this tree diagram for Wednesday and Thursday and Friday, so that'd be 5 stages, then this process would be repeated until all stages have been presented. And then the tree gets really big because like multiple branches going everywhere. It can get kind of crazy when there's lots of stages. All right, so question A. If BB represents 2 straight nights of board games, what does CB represent? CB means card game on Monday and board game on Tuesday. And then question B says, list the outcomes where exactly 1 board game is played over the 2 days. How many outcomes were there? Okay, so we look back at our 4 possible 2-stage outcomes. And they want us to list the ones that have exactly 1 night of board games. So BB doesn't work because that's 2 nights of board games. And CC doesn't work because they don't play any board games at all. But BC and CB, those do work because those both contain 1 night of board games. So I'm going to write BC and CB for a total of 2 outcomes that in which they play 1 night of board games. All right, so let's do another one, this time with probabilities attached. And then we're gonna talk about something called compound probabilities in this case. Yes, I think we are gonna talk a little bit about that. All right, so it says, in the example above, each night's outcome is the result of a chance experiment, rolling the tetrahedral die. Thus, there is a probability associated with each night's outcome. By multiplying the probabilities of the outcome from each stage, we can obtain the probability for each branch of the tree. In this case, we can figure out the probability of each of the 4 outcomes, BB, BC, CB, and CC. For this family, a card game will be played if the die lands showing a value of 1. And a board game will be played if the die lands showing a value of 2, 3, or 4. Okay, so time out. They roll this 4-sided die, right? But it's not really even or fair on whether they play a card game or a board game. They only play a card game. They only play a card game if the die comes up 1. That's it. If the die comes up the other 3 options, 2, 3, or 4, then they play a board game. So there's a way higher probability that they wind up playing a board game than a card game. Well, actually, there's a 3 out of 4 chance that they wind up playing a board game because 3 out of the 4 probabilities outcomes on the die lead to them playing a board game. So B always has a 3/4 probability, which as a decimal is the same as 0.075. And I don't know if you can see this in the video because it's super small text, but right here underneath this B where I'm boxing in, it says 0.075. And it says that underneath all the B's. It says 0.075 right here as well. And it says, and it says 0.075 right here as well. And then since only 1 out of the 4 outcomes on the die create a card game scenario, then that's 1 out of 4 or 1/4, which equals 0.025. And that's what it says underneath each of these C's. It says 0.025 right here, and it says 0.025 right here. And so now we're going to use these trees to help us do something called compound probabilities. And that's essentially the idea that if you know the probability of a stage 1 outcome and the probability of a stage 2 outcome, you could find the probability of the total outcome. So probability of some outcome equals the probability of stage 1, which I'll just say probability of 1, times the probability of stage 2, or probability 2. You might remember in a video like last week, I was saying that anytime you use the word and in probability, it means you're going to multiply those probabilities, and it makes the probabilities much smaller, because when you multiply small decimals together, the product that you get usually gets smaller. So think about like what would have to happen in order to get 2 nights of card games. You would have to roll a 1 on that die and then roll another 1, right? That would be really hard. And so first of all, rolling a 1 is only 1 out of 4 possibilities for all the different things that could happen when you roll this die. And then when you roll it again, rolling a 1 is only 1 out of 4 of the possibilities. And so one way to think of this is that you're getting, the only way to get CC is 1/4 of the 1 out of 4 outcomes, right? Once you roll the first one, only 1/4 of the remaining outcomes that could happen from there produce a CC, a card game and a card game. And so whether you like to think of it as, oh, because they're forcing me to do this and that makes me have to multiply, or if you like to think of it as, oh, I'm only getting 1/4 of 1/4 of the outcomes, and I know that of sort of means to multiply in math too. Either one of those explanations that sort of makes the most sense to you is, or if you make your own understanding in your own head, that's fine. But basically the idea is we take what the probability of the first thing happening, multiply it by the probability of the second thing happening, and that's the probability of them happening together. So here, in order to find the probability of playing a board game and then playing a board game again, well, since the probability of playing a board game is 0.75 in both stages, we do 0.75 times 0.75, and we get 0.5625. This is written right here, but it's just so small that I don't know if you can see it in your in the video. Okay, so just to remind you, these are called compound probabilities when we take the probability of a stage 1 outcome, multiply by the probability of stage 2 outcome, so that we get the probability of the overall outcome. All right, so let's try doing the probability of playing a card game in the first night and then a board game in the second night. So card game probability is 0.25, and we're going to multiply that by board game probability, which is 0.75. I don't know why I'm just now realizing I made this mistake here. I put zeros on all these. Wow. You know what? It's because I think I was having a hard time reading the book because the text is so small. It says 0.25, and I wrote it as 0.0 on all these. All these zeros are wrong. They should just be 0.25, 0.75. Ugh. Mistakes. They happen. We live with them. All right, so 0.25 times 0.75. Well, I know that's 1/4 times 3/4, so I'm going to get 3/16. And 3/16 was that 0.1875, I believe. All right, and then lastly, 0.25 times 0.25. Right now I'm doing the probability of a card game times the probability of another card game to get the CC outcome probability. Well, this is just 1/4 times 1/4, which is 1/16, and that's 0.016 repeating, I believe. Check just to make sure. 1 divided by 16. Nope, it's 0.0. Yeah, I was thinking about 1/6, not 1/16. 0.0625. All right, so let's see here. Question A says, the probabilities for 2 of the 4 outcomes are shown. Now compute the probabilities for the 2 remaining outcomes. Oh, we already did that. Here and here. Okay, so what is the probability that there will be exactly 1 night of board games over the 2 nights? Okay, so let's look at the outcomes that have 1 night of board games in them. There's CB and BC, right? So there's this probability here and this one here that you might not be able to read, but it's the exact same number as this because you're multiplying the same numbers by each other just in a different order, right? And that always comes out to the same answer. That's the commutative property. So the probability of playing a card game and then a board game, that's 0.1875. And the probability of playing a board game and then a card game is also 0.1875. And they essentially want to know the probability of this or that, the probability of card game, board game, or board game, card game. Oops. And or does the exact opposite as and in well, I shouldn't say the exact opposite, but it has a much different effect than the word and when you're talking about probabilities. When you say or, that makes probabilities go up, right? Because if I tell you to roll a die and I say you win if you get a 1 or a 2 or a 3 or a 4 or a 5, every time I say or and I add another option in there, it makes your job easier, right? It makes it more likely that you will win. And so when you have the probability of this or that, the probability of this or that, well, that equals the probability of this plus the probability of that. You just add them up together, right? It's actually really easy. So in probability, the word or sort of just means, hey, add this stuff up. So let's do the probability of card game, board game, or probability or board game, card game by just adding these two numbers here. So we get the probability of like both of them combined. And we're gonna get, what is that? 36, 37, 50.3750. I hope that's right. Let's see. I'm making all sorts of mistakes today, and so now my confidence is all low in myself. Let's see. 375. Yep. Okay. Let's move it on. You know what? No. This video is already long enough, and this page will take quite a bit longer to do. I think you probably get the idea well enough as far as I need you to. So I'm going to go ahead and cut it off there.